Okay, good morning. So let's start. We have the pens. Thanks. All right, so welcome back. We will look at something pretty important. So we'll continue the discussion on Fourier transform properties. Fourier transform properties. And in particular, we'll talk about Fourier transform of differentiation, Fourier transform of an integration. So we know that just like delays and scaling, right? Differentiation and integration are also part of linear time invariant systems. So we can have a system that conducts linear and time invariant operations. Let's say this is x of t. Let's say this is y of t. And this does the operation d over dt. So this is a differential operator. It differentiates x with respect to t and produces a differential coefficient of x with respect to t as a function of time. So we call it y. Similarly, we can integrate x and produce an output y of t, where this is defined as negative infinity to t lambda, where lambda is a temporary variable, or sometimes we call it a dummy variable. So what we are trying to do is, if we have this differentiation and integration operators, right, which are linear and time invariant, can we find the spectrum of y of t in terms of some known quantity, spectrum of x of t? So the question is, if x of t has a Fourier transform capital X of f, what is the Fourier transform y of f? So similarly, this has capital X of f, and y has a Fourier transform capital Y of f. We want to express capital Y of f in terms of capital F of x, capital X of f. So there are some pretty simple ways of doing that, but we will prove it. That will be the scope for today. So let me take a picture. So before we come to the proof or to find the solution, I want to bring to you a new piece of theory called the inverse Fourier transform. So the inverse Fourier transform is the exact reverse of the forward Fourier transform. It turns out that the Fourier transform is a reversible transform. That means you can go from the time domain into the frequency domain, right? X of f. Or if you have x of f, you can come back to the time domain using the inverse transform. So the forward transform is the one that we are familiar with. Let's say forward transform given as x of t, Fourier transform x of f, right? Where x of f is generally complex value. and x of t can also be complex value. This frequency, real value, time, source. So the inverse transform is the reverse. You have x of f and you find x of t. So by definition, the forward Fourier transform is given as x of f integral x of t e to the minus j 2 by ft. We learned that before in class. So the inverse operation is almost the same as the forward operation, but you swap the time and frequency variables and you conjugate the basis. So what you get is, in the inverse version, x of t is equal to the integral minus infinity to infinity, capital X of f e to the plus j 2 pi f t b f. So there's some symmetry, right? If you look at the forward and backwards transforms, x of t is the time function, capital X of f is the frequency function. This is an integral in time, this is an integral in frequency, right? The basis has a negative sign at the top, the basis has a positive sign at the top. So it's a different version of itself, right? They have very similar characteristics. Yeah.
So what does the forward transform refer to again?
The Fourier transform.
Yeah, the forward transform. What does it refer to again?
It's the Fourier transform. This one.
The time difference. Oh, okay. Right. So it's basically the Fourier transform, right?
Yeah.
Okay.
Yeah.
Just a quick reminder, like, what does the Fourier transfer do again? It transfers domains, right?
It transfers from time domain to frequency domain.
That's the only use for it.
Well, that's a big use. It's a pretty big use. Yeah. You don't need any more uses. Everything writes on that, every single thing. So some quick mathematical properties of x. If x of f exists, is defined. We can say that this integral x of t is called the energy. And this integral always maps into some defined value.
Is that I squared? Is that absolute value?
Absolute value.
Oh, absolutely.
So you can also write this as, in complex numbers, x of t, x conjugate of t, it's just notation. So you can either write it as the absolute value, or you can write x of t times x conjugate of t. The same.
And a quick question: what is x conjugate of t?
X is a complex valued function, right? So you can find the conjugate. So by definition, let's say x of t has a real part, r of t plus j times, let's say, q of t. So x conjugate of t is real part remains the same, but there's a negative sign.
Oh, okay. Thank you. That's it. That's useful.
So this is called a finite energy signal, right? You can find a Fourier transform if your signal is finite energy. When you integrate the square of the signal from negative time, infinity time to positive infinity time, you will get a finite value. It won't go to infinity. The other property is that x of t goes to 0 when time goes to plus or minus. So it can't be a signal that goes to infinity at the end of time or at the beginning of time. It has to start from 0 and go back to 0. So functions like tan inverse, which has infinity cusps, right? They have asymptotes going to infinity, don't have Fourier transforms. It has to be a well-defined bounded function that's well-defined so that when you integrate the square, you get a value and it's bounded to 0 at the ends. So the function goes to 0 as time goes to negative infinity, time goes to. So what that means is x of t as t goes to plus or minus infinity is equal to 0. At the end points of the function, solve the 0.
So on the graph, it's gonna look like.
Well, on a graph, you're not ever going to plot it because you cannot go to infinity. But it tends to infinity.
It tends to infinity.
When it tends to, when the time domain tends to infinity, the value of the function goes to 0.
Oh, okay.
Oh yeah, I have a question about the energy part right there. What does that refer to?
So from circuit theory, you know that if you have a voltage, right, you can think of the power is equal to V squared over R, where R is, so if you have a resistance, this is R and there's a voltage V, the power is equal to the square of the voltage divided by R, right? So if you take R is equal to 1 as a normalization, what you really have is a square. So when you integrate power integrated is equal to energy. So this x squared term is something like a power. It's like a power term. And when you integrate it, you get an energy quantity. So when you integrate your x squared of t dt, you get a value that is synonymous with, associated with the energy of that signal. So we call it, because it's finite value, we call it a finite energy signal.
Okay. So M is power.
Yeah, in short. Not power, energy. Integral of power. All right, so let's take the inverse Fourier transform equation. We know that x of t is equal to so this is by definition. So what I'm going to do is I'm going to take this definition and I'm going to apply a differential operator on the left-hand side, right? So because it's an equation, if I apply an operator on the left-hand side of the equation, I have to apply the same operator on the right-hand side by definition because it's an equation, right? So if I go d over dt, I'm differentiating the left-hand side, which is x of t, and there's the equal sign here. I'm forced to do the same thing on the other side. So I'm going to go d over dt, this whole thing. Integral negative infinity, positive infinity, little x of f, e to the positive j 2 pi f t. So take a moment to let that sink in. We started with the definition of x of t as the inverse Fourier transform. So by definition, simple x of t is given as the integral from negative infinity to positive infinity, capital X of f, the Fourier transform, times the basis function e to the plus j2 pi ft df, right? That's the definition. So I take that whole thing and I apply a differential operator against time on the left hand side, right? Which gives me dx over dt. But because I do d over dt on this side, I'm forced to do d over dt on this guy also, right? So I have d over dt, this whole big thing. Okay. Now I'm going to do some algebra and get you the result. So what I'm going to do is that, if I can get my pen's balance, I'm going to write this as the usual thing, dx over dt of t is equal to, this is an integral of f, and this is a variable t, right? So there's only one place where t is occurring. So you can think of this as a two-variable function. It's a function of time and frequency, but the integral itself is defined only in frequency. So as far as this integral is concerned, this time looks like a parameter. It looks like a constant. But over here we have a d over dt. So I can take, because this integral is not a function of t, but it's only an integral of f, I can bring this operator inside. I'm going to go d over dt x of f e to the plus j2 pi f t df like this did. Yes, you can do that, because the reason you can do that is because this is a differentiation against time and this is an integral against f. So they are not connected. Right? So this doesn't know what happened when this came inside. It's insensitive to it. So now I can see that I have a d over dt and there's x of f, but x of f is not a function of t. So this looks like a constant, it pops out, right? So I can write this as, okay, integral, I get x of f, d over dt, e to the plus j 2 pi ft, am I good? Now I have a tricky situation because my integration is df is against frequency, but I got this d over dt thing inside, and that's operating on the t over here, right? So it's operating, it sees this t because this is a function of t and there's t over there, right? All the other stuff is insensitive to this t because it's not a function of t. So because of that, I have to differentiate this guy against time, which we know. So let me write the answer. It's a little tricky until you get the hang of it. So I'm going to write the answer here. So integral, this remains the same, x of f, right? When I differentiate e to the j2 pi ft against t, this 2 pi f looks like a constant, right? So I get j2 pi f out then e to the plus j 2 pi f t df.
Could you put the properties of the of the derivative of the e? So yeah, just as a quick refresher.
So e to the alpha x over dx is equal to alpha times e to the alpha x. So now I have a function, right? I have x of f, j 2 pi f, this whole thing. And this is a function of f, this is a function of f, this is the Fourier transform basis component. So I can group this whole thing into a new function, x1 of f. Where x1 of f is simply x of f times j 2 pi. So what do we got? We have d over dt x of t, right? Is equal to x1 of f
I understand where you got the x1 of f, but isn't x1 of f don't it need a exponential to be at the bottom to be a Fourier transform?
So we do have x of f is the Fourier transform, right? X of f is the Fourier transform of simple x of t,
Okay.
right? But I'm modifying it by j2 pi.
Oh, got it.
Right?
Okay. So if it was a t, then you can't do that.
No, but it's not a t.
Oh, got it. Okay.
So what we are saying is that this is an inverse Fourier transform, right, of x1 of f, and it gives d over dt of x of t. But x1 of f is j2 pi f times x of f. So it's a little convoluted, but if you think about it, what it's really saying is that the Fourier transform of d over dt of x of t is x of f times j2 pi. So we can write the Fourier transform pair if x of t as a Fourier transform x of f, then d over dt x of t as a Fourier transform pair j 2 pi f times. That's the theorem. So if you know a Fourier transform of some x of t as some x of f, you know by just differentiating the time version x of t, the Fourier transform is simply going to be whatever the Fourier transform x of x was times j2 pi. You just stick a j2 pi f in front and you're done. So that's a property of the Fourier transform. Fourier property. So let's put it this way. So let's say we have LTI system. This LTI, you send a P of t and it produces a P of f. Right. If I take a copy of this and put this into a differentiator, d over dt, right? And then I tap this one, I scale it by, let's say, alpha, scale this by beta, and I add them up. What's the Fourier transform here? So I can write Fourier transform of the first one is P of f, right? Fourier transform of the second component is what? J2 pi P of f. So the total Fourier transform is P of f alpha plus beta. You can write down the answer by inspection. So the proof is a little tricky, but once you get through the proof and you know the result, you can ding, 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 apply the result very, very fast and do complex connections of various blocks by applying the theorem over and over again. Like, you don't have to keep proving it.
I'm a little confused. So the P of T goes through the LTI system and it comes out as P of F. Which
Yeah, it's just notation, right? I just replace small x with small p and capital X with capital P. So you can call it what you want, but the point is that P of T has a Fourier transform capital P of F, right? So when I do the differentiation of P of T against time, I get the Fourier transform P of F multiplied by J2 pi F, which is what we proved. So we have a P of F component scaled by alpha, a J2 pi F times P of F component scaled by beta, and I'm adding them up. So the combined Fourier transform is the common part P of F times within parentheses alpha plus beta J2. It's just algebra.
Okay.
Yeah.
Okay, so if I understand this correctly, this right here is basically the Fourier transform of the derivative of
Exactly.
x to t, right?
Exactly. Yes. Perfect.
Okay.
So we could have used the forward Fourier transform equation to prove that result, but the algebra is a little more tricky. Using the inverse transform is easier to understand. But you can use the forward or the reverse or the inverse. Okay, so let's do the same proof for the integral version. So now what we have is we have an integrator, right? Box that goes minus infinity to t x of lambda d lambda. So if x of t has a Fourier transform x of f, what is the Fourier transform of x of t? Call it x1 of f. So all these differentiators and integrators can be built using circuits, right? You can use op amps and other things to build. The simplest form of integrator is a resistor and a capacitor. So you can have a resistor, capacitor, and an op amp.
Differentiator is the other way around.
Yeah. So we start by the definition of inverse transform. X of t is defined as So the proof goes something like this. So you take x of t, but you actually integrate it. So you go from negative infinity to t, x of lambda, d lambda. So this is a temporary variable. It is equal to integral so I can swap the order of the integrals minus infinity to infinity, minus infinity to t, so lambda.
Just so to get a clear understanding, the one that you did before was for differentiators.
Now we are doing the same thing for integration. Yeah. So again, minus infinity to t x of f. I'm integrating e to the j2 pi ft. So earlier we differentiated, now we are integrating. So when we integrate, we get a j2 pi f term down. And it's got some limits. E2 So there are some calculus details which we won't get into, but finally we get this j2 pi f term out. So we can write this as x of f So basically what it comes down to is, simplify, we have x of t integral as a Fourier transform x of f divided by it's kind of simplified. There are some other little calculus things there which I have ignored for now. We can come back to that later.
I have a quick question.
Yeah.
So you integrate d lambda.
Well, not yes d lambda, because we are trying to find a function of t. So at the result of the final output of the integral should be a function of t. So you can't integrate a function of t to get a function of t. You need some other thing, right? So this lambda is a temporary variable. So when you integrate this from minus infinity of time, which is now called lambda, to the present time, which is right now t, then what you get is a integral that's a time function.
So okay, it's like a substitution basically.
Yeah.
But
Yeah.
now here's the part that I didn't understand.
Yeah.
What variable should I think is the variable that's being integrated? Like, how do I know that t is the variable?
So this is a two-dimensional integral, right? And you have df and d lambda here.
Yeah.
So as long as there are no two variable functions, you can swap the order of the integrals. So that's why I can swap the order of the integral, suck this one in, because x of s does not have a function of lambda inside. And then this looks like a constant, it comes out, but this part has t, because the result of this integral has t on it. So I have to apply the integral and apply the limits to it.
Oh, so T is the one that's being.
Yeah. Well, t is the result, right? So once you integrate it from negative infinity to t, you get this component function formula.
So why on that one, why do you integrate it, but you put it under, like, why wouldn't it just?
Because the integral of e to the ax is e to the ax over a.
Oh, I was thinking about the.
So there's a little bit more math to it, but I kind of put the simplified way. We'll first follow the simplified one, and then we can talk about more complex details of these things later. But right now, the basic thing to understand is that if you have a function x of t, which has a Fourier transform capital X of f, the integral of x of t simply brings the j2 pi component to the denominator, right? There could be some additional stuff here, depending on what it is that you are doing, but ignore that for now. And these are very deep things if you want to go deep into the calculus, but at this level, for your beginning level stuff, we are just going to simplify stuff a little bit. So just go with the flow, and this is good enough for now.
What other classes do we need, like, understanding of this?
Which, communications. Yeah.
Question about the circuit.
Yeah.
So how do we get the circuit from the integral?
Okay, good question. So let's do that. The impedance of a capacitor is 1 over Cs. This is Laplace. Have you done basic control systems somewhere? Anybody done Laplace? You have? You have, right? Everybody done Laplace transforms?
Yeah.
All right. So this is the Laplace variable, right? So this has S is equal to sigma plus j omega, which is equal to sigma plus j 2 pi. So when you go from Laplace transforms to Fourier transforms, what you do is you set the real part of the Laplace transform of the S variable to 0. So if you take the Laplace S and put the real part of the S to 0, that means sigma is equal to 0, which gets you j2 pi f. One second, let me finish. So the impedance is given as 1 over Cs. So your gain of this whole thing is equal to negative Z2 over Z1, which is equal to 1 over RCS, negative J2 pi RC. So this is a constant. You get 1 over J, some constant times T. Yes.
Oh, I was gonna ask, could you like full derivation of the plus? It's like I understand how you got that.
Yeah.
Doing on electronics, but
It should be covered in one of the courses, but it's just not covered in this course because we don't do detailed Laplace. There's simply not enough time to do it. So we'll summarize. and we'll do a problem. So we have a circuit which has 3 op amps. Okay. The first op amp is simply a gain stage. Second op amp is a buffer tapped by a voltage divider, right? The third op amp is an integrator. So this is an integrator. Buffer, scaling buffer. This is an amplifier. So I'm asking, if I have such a circuit in a breadboard, let's say in the lab, and I produce some input x of t, which has a Fourier spectrum capital X of f, that thing produces an output y of t. Right? So this is a y of t time domain. So this is frequency. It is done. I'm asking you to find or write down an algebra expression of capital Y of f that is in terms of capital X of f and all the other circuit components in the circuit. Right? It's a function of all of them. So how do we do that? You can keep writing down the spectrum starting from the first point. So here the spectrum is X of f. Right? What does this thing do? This will scale the amplitude by 2, but it has a negative sign because it's an inverting amplifier. So because of that, the spectrum here is negative to capital X of. This is the gain. So now I'm applying negative 2 capital X of f in the frequency domain. That's a spectrum. This is dividing it equally by half because it's a voltage divide. So if I divide negative 2 X of f by half, I'm going to get negative X of f. What does the buffer do? It completely copies over whatever the signal that comes here to the output, no change. Right? So because of that, the spectrum here is negative X of f.
Wait, so the buffer, doesn't buffer add 1?
No, it does not add 1. It has a gain of 1. So when you multiply something by 1, it's the same thing. It doesn't change anything. Yes.
How did it work? So What, again, where's the -2 come from in the game?
Because this is an inverting op amp, right?
Uh,
So if you find the transfer function of this circuit, have you guys done op amps?
in circuits.
You have.
Yeah.
So this has a gain of R2 over R1. So R2 is 2R and R1 is R. So 2R divided by R is 2. But there's a negative in front because of the way it's connected. Yeah.
Voltage divider, I understand the voltage divider part, but when it goes to the buffer, isn't it a non-inverting op amp?
It is. So whatever the voltage here, let's say the voltage waveform is V of t, some waveform, is still the same here. It doesn't change. So it just looks at the divider point here and applies it over here without change.
Okay.
Yes.
Okay, so if I understand how you got the gain for this, basically you divide the amp three you divide on this one you divide this one over this one, right?
Yes. And there's a negative in front.
All right.
That the negative comes from the fact that it's connected in this particular way.
So
Yes.
Just a quick.
Go ahead.
I can think of the buffer as just something that takes it's just the continuous line.
It is, and yes and no. Okay. So the reason why you need that is because there's no current flowing. The current here, I is equal to 0. Because it's an ideal op amp, it has infinite input impedance. Now, if I didn't have the buffer and I directly connected this node to this one, this will have a loading effect on this circuit because it's now all one bit circuit. So I can basically copy over the voltage here without this messing up that one by having the buffer.
So can I define it as it brings the voltage to the output, but it cancels the current, so it's not a complete circuit?
Yes, it's an active circuit. It is a complete circuit,
Yes.
but it's defined in a way so that it copies the voltage, but it doesn't allow any current to flow from this node to the other.
Because if you were, then the derivation would be very hard.
Not very hard, but more harder than this. but so the current for this still comes, but it comes from inside the op amp. It's got a circuit for that. It doesn't come from this. Right. So this is called a voltage controlled voltage source. Voltage controlled voltage source. Or voltage controlled voltage source. So VCVS. All right, so negative x of f here, but we just found out that by having an integrator, the only thing it does is that it adds a 1 over 2 j2 by f at the bottom. So the spectrum y of f is going to be whatever the input, which is negative x of f divided by j. Done. Yes.
CC, can I ask how you managed to get the negative x f at the end, the scaling buffer?
Yeah. So remember, this is x of f.
Mhm.
-2 because the gain of -2 will give -2 times x of f, right? So this is -2 times x of f.
Mhm.
This is R over R. So the voltage here is R over R plus R, which is equal to half. That's a dividing fraction, right? So when you apply half times -2, -2 times half is -1, which is equal to negative x of f. Yeah.
So if it wasn't put into this circuit form and just put into like what we've been doing for the regular LTI system,
Yeah.
it would just be a.
Oh, this is a regular LTI system.
But it is more complicated than the regular, rectangular.
I mean, I could have drawn this as a bunch of boxes if it makes you happy.
Yeah.
But it's the same.
The boxes, it looks, it's the last version, right? It's the
Right.
most derived.
This is the circuit,
circuit. but
whereas the box is a signal flow graph.
Yeah.
But the circuit and the signal flow graph are essentially the same.
Could you do, if it's possible, could you maybe do like a quick drawing of like the ones with the boxes?
Yeah. So the ones with the boxes will be, okay, so the first box will be negative, let me redraw it. So the first box will be -2, right?
Yes.
The second box will be half. Correct?
Yes.
And the third box will be
And these splitters, like the ones that split into two,
Mhm.
how does that look on a current? So it's just like,
so it depends on whether you're splitting voltage or current. If you're splitting the voltage and the whatever that you're connecting to is not loading, the voltage is copied over, right? But if you have a node and you are pushing current, then the current, all the currents have to sum to zero from the Kirchhoff current law.
so
So this is all voltage mode. We assume that the op amps, the reason why we use an op amp is because op amps have zero output resistance. So it can spit out as much current as needed in theory. In practice, no. But in mathematics, an ideal op amp can give any current it wants. But in practice, as you will find out in the lab, if you try to do it, you're going to fry the op amp. So it can only give so much. But for just simple modeling, we can just do this. Okay, I'm going to stop here, but you can continue the questions. Yes, sir.